All right, good morning. So let's pick up where we left off last time, and we were talking about vocal messages, and we went into like how we can use our voice to express emotion, attitude, and so on. And we even talked a couple of things about like how we can use voice assessment for example, assessing a person's mental status. And we identified that there are basically three layers of vocal messages. On one hand side, we have the linguistic layer. We really didn't talk too much about like the semantic information that you can convey because it's kind of natural in language. And we have an entire lecture on verbal messages and communicative aspects. We then talked about the paralinguistic layer, where basically we can convey emotion, we can convey mood or attitude through like a overlay of the on top of the linguistic layer to modify this layer. So we talked about prosody. Today we're going to talk a little bit more about voice quality, which I've done here. And voice quality, I think, is very interesting because it's really like a very flexible tool, and it's used in so many aspects of our communication, and we don't really like actually know that we're changing it or use it in many ways. And then we said that there's an extralinguistic layer. It's kind of like the layer that we might not be talking about too much in the future, and we might not be too interested. It's kind of like this context kind of area. So on the one hand side, you want to know about gender, and age, for example, but if you have a classifier that tries to identify emotion, you might sometimes actually want to separate a model for female voices versus a male voices, so that you can actually learn the aspects that are unique to the two, rather than some like differences in gender. So these are often kind of like noise going into your classifier. You want to know about them, you want to predefine them early on. We then talked about the fundamentals of speech. We identified that there is like a cognitive planning phase in speech production and then the motor actions. We talked that it's very complex and it's actually one of the fastest movements that the human body can do. And we also identified that this kind of sequence and program can go wrong in individuals that, for example, suffer from psychomotor retardation, which is a symptom of depression. So speech production involves a continuing cognitive processing, and it is very it's a very interesting motor program that on the one hand side you need to build the verbal content, but then also your emotion influences this motor program voluntarily and sometimes also involuntarily. And the involuntary aspects are often associated with voice quality, for example. Then we talked about how we can use, for example, our tongue to form vowels, and that the tongue positions are very important for the vowel production. And we identified a few that we can plot those on this vowel space kind of display of the two dimensions. On the one hand side, you have the first formant, and the other you have the second formant. And basically, these are the resonance frequencies of our vocal tract. And we identified that this vowel space can be reduced in individuals suffering from depression when compared to individuals that don't. And so it's kind of like this this process that I wanted to introduce, in a sense, that like starts off at, okay, we have something in mind, like we hear psychologists talk about individuals suffer from depression. They are, like, if they are suffering from depression, they are more monotonous, they are less expressive in their speech. And so if you hear someone say something like that, you feel like, okay, I want to find this in my data, and then you start looking, okay, so what is out there? Like, what's the literature say? Well, for example, motor production or like speech production and the motor planning for speech is complicated, it's difficult, and it could be impaired. So you start thinking, okay, like what could be something that is impaired? Well, it might be the vowel production because the tongue movement is quite complex. And it's also something that's large enough for me to measure, right? So these measures are actually not that hard to get. And so this is kind of like this process of, okay, let's identify a problem. What is my data? What can I find in my data? What do others say about it? And then you try to like design a feature, design an approach around this. And in our case, we designed a nonverbal, an unsupervised approach to identify formants. And this is our example here, where we said like the medical relevance is important. You remember these triangle plots here that I showed you guys. And actually, it's not only relevant for depression, but also for other motor disorder disabilities. And it's not working anymore. And so yeah, we identified psychomotor retardation as one of the indicators, and then I showed you these two plots where on the one hand side you have an individual that's not depressed, where the green triangle is the individual's triangle and it almost overlaps entirely with the red triangle, so that kind of like shows this person's vowel space is sufficiently large and it corresponds to the reference population. While if you look at an individual's person, you see a lot of observations in the middle where there are actually no vowels that you should utter in that range, so that gets pulled in. That can be associated with slurred or with slurred speech, for example. Then we went on and talked a little bit about the anatomy of hearing and how sound waves basically enter our ear and ultimately end up in our brain for us to understand what is being said and how the words are, or like how these three layers of vocal messages can be decoded. We talked about the outer ear as a very nice like directional filter. It allows us to hear directional information. We talked about the middle ear and the three ossicles there, and then the inner tube that ultimately ends up in the cochlea, which we identified has different perceptual ranges, where high frequencies in which humans do not speak, so from 20,000 hertz to 7,000 hertz, we have like this tiny part there in the cochlea that is responsible for this. But then if we look from 200 hertz to, let's say, 1,500 hertz, we have all this curvature here that is responsible for that. So this is a clear indication that obviously something is important in those frequency ranges and not so much up here. You can imagine that, for example. It's similar in other animals that communicate, for example, in very different ranges of frequencies. So, for example, bats have like a much higher resolution in the higher frequencies, and also hear in much higher frequencies, or dogs. And for us, it's more these lower frequencies where our voice is usually at. For a reference, and I don't think I said that, but for a reference, like what you would expect individuals to speak in their fundamental frequencies when we talk about the vocal fold vibration. These happen at the lower range, about 70, 80 hertz, up to like 500 hertz in kids. So that's kind of like the fundamental range. And you can see that that is actually covered by this very high resolution kind of filter there. All right. Then we had a bunch of examples about prosody, and I brought back my 50 Shades of Yeah, and that's mainly to test if the audio is working, but let's try it out. So again, I just want to illustrate through this that there are, you can have the same verbal message over and over and over again, but it means something different every single time. You can convey doubt, you can convey that you are convinced, that you are in agreement, that you are happy about something, or angry about agreement, or something like that. So here we are. I didn't bring both again, so don't have to live through that too much. But yeah, so this is one single person, one single conversation, and you can imagine that there is a lot more out there in that sense. So this is really one of the difficulties that we have to deal with, where if you just investigate text and you just want to understand like a sentence or a book, well, books are sometimes more complicated, but if you just want to understand a sentence and that's the only information that you have, you can tease apart everything in the verbal content. But if you have that same sentence spoken and you have it spoken in different prosodic sequences, or you have it spoken in different voice qualities, it could have different meanings, and your interpretation might end up to be very different every single time. So that's one of the difficulties that we are dealing with. And really you need multimodal information to be able to disambiguate those kind of situations. And that's one of the reasons why we are interested in multimodal machine learning and multimodal data processing. All right, so then we said, okay, there are a few characteristics that I can list up, and that these are like some different types of features that we can look at. So for example, that's kind of like pertaining to speed, or like like how fast the words come. Here, this is more about the fundamental frequency, and you can already see that fundamental frequency is not just one feature, but you can look at a lot of those. And we had actually a bunch of these like slides about trajectories of the fundamental frequency, where you can pose a question if you have like a little rise of the pitch, or you can have doubt if you have a rapid rise at the end of pitch. And so you might also be interested in like the first derivative, so like what is the slope of the pitch contour, and but you also might be interested in like what's the range, like what's the lowest and what's the highest, and you might want to know like, okay, so what's my median frequency, and then like is the range like more wide, or is it flat? And so there are a lot of different kinds of features, and there's this one feature extraction toolbox. It's called OpenSmile. I'm going to introduce it on Wednesday. And so those guys, they basically extract for every single feature, like fundamental frequency or intensity, they extract about 50 different kinds of functionals. So the min value, the max value, the 10th percentile, the 50th percentile, which is the median, the 90th percentile, and many, many more. And like the deltas, so that the first derivative, and the deltas, the second derivatives, and so on. So you can go about with this like in very excessive ways, which I'm not necessarily recommending right away, but you can look at a lot of these features in very different ways. So then we had a couple of examples. So for example, happy here with increased fundamental frequency, mean and deviation and range, but also increased intensity. And you can imagine if you think about like a happy moment, you shout something, you think it's happy, or like you're expressing happiness, you get louder. So this is
10 talk.
All right. And then with anger, Well, on this scale, we don't really see much difference between happy and angry, and actually, this is one of the difficulties here, that this is like literally the only one that you can imagine, or that we find on this like on these two scales, and then we find a little bit here, but so anger and happiness are two voices that are, from a standard viewpoint of prosodic analysis, are not easily distinguishable, and you can see that a lot in papers. Oops. All right, and what is actually different between the two is their voice quality, and we're gonna talk about voice quality in a second. So you kind of need a different set of, like a different lens to disambiguate them, and prosodic features are not necessarily the right way to do this. All right, some sadness. All right, this is a bit too sensitive. All right, and then we looked at a few of those trajectories. So that's the neutral voice. So you hear this pressed voice of high pitches and high intensity. And some fear. So where you have this more breathy kind of voice. And yeah, so this is kind of like what we're going to talk about today a little bit more. All right. Then we went briefly into nonverbal vocal expressions, and we covered mainly some laughter, and we talked about pause fillers and back channels. And so, again, the process that I would like to introduce is, in a sense, like we identify a problem, we identify the characteristics, and we see, okay, there is some distinct prosodic and vocal characteristics of laughters that we want to look at and that we want to identify, and I think you've read a paper about that. And then once you know all about your data, you start to think, okay, so what is the approach for me to go to identify automatically based off of some machine learning or feature extraction process, like what laughter sounds like and if I can find it again. One of the biggest reasons also why I'm interested in laughter is because it's also multimodal. It is shown in your face, in your gestures, like when you have your head and the upper body move rhythmically at the same time, and you have an acoustic representation. But also, laughter is very interesting in the sense that it kind of can range across many different meanings. So you can have humorous laughter, you can have sarcastic laughter, or nervous laughter when you smile at your boss or someone that you want to kind of like show that that they are kind of funny even though you think they're not, or you want to kind of like build a relationship, and so laughter is very important in that sense. Okay, and then we looked at a few of these laughter bouts, and we had talked about how the narrowband and the broadband spectral analysis give you different viewpoints on the same data. And you can see that this is kind of like this rhythmic kind of pattern. And one of the machine learning algorithms that actually worked pretty good in my investigations in detecting this is actually one that tries to find these patterns in the data. We might be talking about the echo state networks at some point later. And then we had our pause fillers, the hesitations, the pauses, and in this case, what we were interested in was basically something called spectral stationarity, and we see in this case, for example, this is like a second and then nothing, and the spectral stationarity measure down here is very high for as well as for the pause. Well, obviously because in the pause case there's only noise, there's no actual other source of information, and for the spectral stationarity is very high. That means basically that not much changes in the spectrogram, and you can calculate that basically with a different set of tools. So for example, you could calculate the entropy, you could look at like the distance between your spectrogram frames from frame to frame and kind of like look at that, or you could look at the derivatives and so on. So there are many ways to get at this measure. I actually think, well, the way I measured it in this case is more or less like on a frame-wise basis and subtracting the spectrogram from each other. All right. So, are there any questions until now? Because we're going to move into the voice quality part now. That's where we kind of left off last time. All right. So voice quality. We had a couple of examples, but I really would like to bring that back because I think voice quality is very important, and it has nothing to do with like goodness, even though the word quality comes up. But it's about like the coloring of the timbre of the voice, and it can be used in many ways. And I got actually two examples, and I don't know if anybody speaks Gujarati, but so there it's very heavily used there. And I brought an example here where the word, for example, is bar or bar, something similar to that.
Bar. Bar.
And in one case it means 12, and the other case it means outside. Something like that, right? No? Well, that's what I got from the website. Oh, you can look at it. Oh, wait. So it was these two, and you're saying it's not?
We don't see it.
Oh, you don't see it? Oh, God.
Like it's different. I don't know.
So it was these two samples here. You can play it again.
Bar. Bar.
Some people hear the difference? So that's another issue about voice quality. Voice quality is very subtle. You can change it in a way that individuals not necessarily hear it directly, but it is something that's happening with your voice, and machines are actually pretty good at picking it up right now. And so we developed a set of features, and I'm going to introduce those features also on Wednesday. And the feature extraction method, it's called CoverRep. It's our toolbox that doesn't extract all these kinds of functionals, but it extracts like 15, 20 voice quality features and a bunch of other features that other toolboxes don't have, and they're a little bit more like targeted to understanding voice quality. Voice quality can also, in contrast to just disambiguating words, like say, having a different meaning, or maybe not, they can also be used to convey attitude, mood, social factors. I'm going to show an example of this where the typical Valley Girl kind of language comes in, and then turn management is also kind of interesting in Finnish. In Finnish, you can basically change a turn by changing your voice quality, or like basically identifying that now is a good time for me to yield the floor and provide it to the next person to speak. And so the entire vocal tract is responsible, whereas the phonation and the manner of the vocal folds vibrate are playing a major role for the voice quality to be conveyed. So what you want to look at when you are identifying voice quality differences, you want to look at the voice source. So we talked about that the voice source kind of ends at the vocal folds, and then we have the vocal tract filter that happens afterwards. And so you really want to get rid of the vocal tract filter, because that almost covers the entirety of like what you want to look at. So the vocal tract filter mainly is responsible for like also the verbal content, like the forming of the vowels, the click sounds, the stop sounds, or the fricatives. So you want to get rid of this because you just want to listen to the voice source. Oh yeah, whisper is also voice quality, but in whisper the vocal folds are not vibrating. So that's the difference there. Alright, so we want to look at the vocal folds. So that's the main target here. We look at the vocal folds, and this is a section if you look on top of them. And basically what we're interested in is the dynamic of the opening and closing of the vocal folds. And what's happening is the following. You're going to see those shapes over and over again. So you, in the position, like you start at the closing position, so no air is flowing through the vocal folds. The vocal folds are opening, you're entering the opening phase, and then the vocal folds are closing again. They are not perfect machines, so they overclose a little bit, so there's like a discontinuation in there. They hit each other, and then they go like this, and they go into a resting phase, and they open again. So this is kind of like the phase that they follow. And the interesting part now is the dynamic of this phase. Like how are they hitting each other, how fast and how slow are they opening and closing. So the speed of opening and closing is kind of like relating to the fundamental frequency. That's your fundamental frequency. But then if these vocal folds, like in a guitar with the strings, if they are like tied up very heavily, they're tense, and that's when the shape changes, whereas when they are loose, they can be more in the breathy kind of voice. And so the tenseness of the vocal folds is directly related to the voice quality. And they are actually a muscle, so you can kind of like they're connected to a muscle, you can pull them. And so that's kind of like what changes the voice quality. Alright, so we had a couple of examples for breathy voice.
Where were you while we were away? Where were you while we were away?
That was modal and then tense.
Where were you while we were away?
And for a female voice.
Will you lie low?
No, this is still here. Okay.
Will you lie low? Will you lie low?
Alright. So these are the three kind of like voice qualities that most people work with, and this is kind of like on the breath to tense dimension. And you can imagine that this is not like necessarily a very discrete kind of separation. There's more of like a continuation going on. So you can kind of dial up the spectrum on how breathy or how tense you want to have the voice. There are others that are not necessarily on this dimension, but for example vocal fry or the creaky voice, which is very interesting because it actually is below the fundamental frequency that I said earlier as like usually the lowest one. So that is because the vocal folds are very loose and they just like flap around a little bit. So it sounds kind of funky. So let's have a listen to how she sounds.
There's an epidemic in America. Epidemic. It affects young women. And that is vocal fry tones. Ugh, gross. Hi. So, what's going on in this country is something that really irritates me. And that is vocal fry tones, especially heard with young teens or people in high social groups.
Alright, and so we don't have to listen to the entire thing here. But basically, this is how vocal fry looks like on the spectrogram. Basically, you see these like sudden bursts here, and they're usually, as you heard in her, like usually towards the end of a sentence. I have had like a phase when I was looking at this a little bit too much, and I started to talk like this. It was pretty awful. But also, what I would like to share with you here on this slide, in a sense, is also that, so you can see the fundamental frequency is kind of stable around here, and then it goes up, so it jumps to like 300 or something. And as you just remember, like I just said, that vocal fry is actually characterized by a very low fundamental frequency. So vocal fry tones or creaky voices are actually really hard for classifiers to work with, because what we like track in these more periodic phases where we look at fundamental frequencies, we look at periodicities, like kind of something that repeats like in a regular basis. But here you enter like a phase where a lot of noise just gets bursted in. And so that makes it quite difficult for the fundamental frequency trackers. So it's just something to keep in mind. Thankfully, this is not happening too much, so you don't really have that problem on a regular basis.
Gad, do I remember it?
Oh, that's the voice here.
Gad, do I remember it?
So he has it towards the end, he has the vocal fry. All right, so this is kind of like now how these pulses look like that we want to investigate, and what their shape is, and really this is what I explained earlier with the vocal folds. So you start off at a closed phase, so they're closed. You're entering the open phase. This is basically glottal flow. Glottal flow means like how much air is going through the vocal folds right now. Okay. And so glottal flow, the air is going through. It enters like the most airflow when the vocal folds are open the widest, and then they close again. And here's this discontinuity where the vocal folds basically hit each other. It's kind of like an excitation here and this is the derivative of this signal here. So this kind of like amplifies that there's something. Some discontinuation going on. And then they close again, they loosen up and basically enter the closed phase again up here, and then the whole thing repeats. And the good thing is that this is kind of like repetitive. A number of features that we are interested in here, these parameters that are the Lillian-Constant parameters, which basically, on the one hand side, you have the fundamental frequency, which is basically 1 divided by this length here. So this is time tc and time t0. So this is like the pulse length. EE is this excitation. This is larger in tense voices. Then you have RG, which is 1 divided by TP, which is this phase here, and this phase is which one? It's the opening phase, exactly. And this is also in relationship to the fundamental frequency. Then RK, you're looking at basically, what is this? E. Yeah. So this is basically the opening to closing phase minus the TP, which is basically the relationship between the opening versus the closing phase, and TA times TF is the refactor, or like the relaxation phase, like how fast does that go in relationship to the fundamental frequency. You can already see like everything is kind of like dependent on the fundamental frequency, more or less, because there is a direct correlation between tense voices and high frequencies. It's just like because of the physics that happen, because if you have a very loose vocal fold, you can't have them vibrate in a very high frequency. All right? Cool. So a couple of features that we are also interested in are, so for example, this one is the normalized amplitude quotient. which basically is the glottal flow, the amplitude of the glottal flow, divided by like how deep this continuity goes. So that's kind of like EE in that sense, and then also in relationship to the pulse period or the fundamental frequency. So that's one of the parameters that we're interested in. And I would like to introduce the second one, but before we do that, I would like to also mention that the Lillian constant model is very precise, and it is quite difficult actually to extract all those parameters from the voice signal, and it takes a lot of time. So it's like we have developed quite extensive optimization algorithms that try out everything. It's almost like, I don't know if you've heard about it, we'll get to it, but the Viterbi algorithm, so they follow like a dynamic programming kind of approach where we try to identify the path of least resistance, so to say, to learn what these parameters are. However, we also introduced, and this is kind of like something novel that no one else has done before, where we said, well, if we can front load all the training and all the optimization onto like an earlier stage, and in real time we don't have to do this anymore, wouldn't that be fantastic? And we thought, oh yeah, absolutely, that would be fantastic. And the one method that came to mind that always front loads all the work, and then once it's learned, it's literally a matrix multiplication, it's neural networks. And so that's why kind of like you're all here in a sense, I think. And so what we did is we actually learned to extract those parameters in the neural network. So all we had to do are these 3 steps beforehand, and basically identify like, okay, so when do we expect voicing to be happening, do some filtering. It's very cheap. This you can do like in, I don't know, in a fraction of real time. And then you like throw it through this neural network, and the neural network spits out like your Lillian constant model parameters. So that's what we tried to do. And so this is what we ended up with, and this is just an example. So if you want to do this, you need really good ground truth data. And how do you get ground truth data about voice quality? Well, you either cut off somebody's head and you just look at the vocal folds, or you do something like this. And basically, we have a microphone here on that side, like where we record his voice, and we have basically a microphone. In this case, it's an electroglottogram down here that records the vocal folds. Okay, so and this is basically a derivative of the electroglottogram, and this is the glottal source that we could derive from this, and you can kind of see this idealized LF parameter kind of sequence where you have a rise, you have the rapid downset and the up, and then you have this repeated. And obviously it's not as smooth as the model parameters suggest, but it fits quite okay. So this is what we want to build in our neural network, and we hope that using the ground truth signal from the electroglottogram can help us achieve this. So this is what we did. We experimented with 3 different data sets. So we learn on 2 data sets. We compare our work with 2 different other approaches that we have implemented, and we tested on an independent data set that none of these approaches has trained on or has seen before. And so we train our neural network, and it looks like this. So in this case, we just extracted MFCCs and deltas, and and then we extract only one parameter, which is basically the open quotient, which is from here to here. And we train on 2 sets, and we test on the 3rd data set. And what we found is that in all the cases, our model is outperforming the other approaches, and so we're kind of happy about this. This is the first kind of result about this, and then so this is the actual opening, closing, opening quotient measurements for breathy, modal, and tense voices. You can see that the open quotient is higher for breathy voices and lower for tense voices with a higher standard deviation. And our model kind of follows this quite precisely, while others completely overestimate or fall flat in a sense, and actually have it the reverse way in the extraction. And what we also found is that our approach seems to be outperforming the other methods on different kinds of speakers. So in this case, the Yaga approach actually is outperformed, like the Strikalev approach is clearly outperformed by us on speaker 2 and 5 in the Arctic dataset, and for speaker 3 and 4 we're outperforming the other approach, and that kind of like shows that we are more speaker independent, or more generalizing, or better generalizing than the other approaches. But what is actually one of the most interesting, or like the most important parts why we did this, is actually we wanted to find out if we can kind of break the barrier to employ this as real time. And so if you think of like 1 second of speech, our approach requires 0.4% of real time. That's like for 1 second of speech, it requires that much time. And yes?
Do this approach need to be individualized? I mean, collect the data from multiple person, or just one person?
Sorry, can you repeat the beginning of the
I
question?
mean, you talk about this approach needs to be ground truth, and you need to, and is according to other measures, is it individualized? It depend on person, or use multiple person?
Right. So our approach is, and all of them are generalizable on all like individuals, but so this is actually showing that we're outperforming them on different speakers. And these are speakers that we've never seen before.
On testing, you test on different speakers.
Yeah. And you have to do that, because otherwise you might just overfit on one person, and so these are all pretty small data sets, unfortunately. But the problem is that you don't have electroglottogram for a lot of data. Like nobody usually gets that. But yeah, in comparison to the other approaches, which require 15% of real time, or even 200% of real time. So that's kind of like the area where we need to get to improve on this. Another thing where breathy or tense voices are becoming important is actually in the assessment of mental status, and this is from our other work, where we identified that individuals with depression have actually got tenser voices in our data set than individuals without, and that's kind of like an interesting finding that we had here. So we also didn't see any statistical differences between males and females, which is also very interesting, because as you can remember, the prosodic measures like fundamental frequency and so on, they are actually quite dependent on gender differences. These guys are not so much. I would like to give a little bit of like a little kind of outlook into doing some machine learning. And so we utilize these voice quality parameters to detect depression, no depression in our data. And the one method that we use in this context is a support vector machine. I'd like to introduce kind of like the idea of a support vector machine very briefly. In this case, support vector machine tries to separate the red from the blue class, and what it does try to do, and is why it's so popular, is because it tries to maximize the distance between these points here on the margin and the hyperplane that separates those two. And so this is very high level. We're going to go into more details soon, but support vector machines are popular because they follow this kind of principle. Well, we identify a decision boundary. We only need to look at support vectors that lie on the margin, and we don't have to regard these other data points back here. And there's always a global solution. So that's kind of like just very broad why support vector machines are so popular. So all of these lines here, in a sense, are actually valid separation hyperplanes. They separate the blue and the red class perfectly, but they are not the optimal solution. And so why are these not optimal?
The hyperplane doesn't pass through the middle of the boundary.
Right, exactly. So it doesn't separate them with the widest margin, and widest, like, so if I change, or if this is not all the data that I've seen, but maybe I didn't see a data point here, which is a red square, so that hyperplane here would already make a mistake. So it's very error prone. It's prone to noise and so on. And so intuitively, you want it to like go through the middle with the widest margin, so that you have the most like space for error. All right, and yeah, so you want to find a hyperplane with the widest margin, and the intuitive explanation, like why there's only one with the widest margin, is because, well, you can fit many different ones with this wide of a margin through here, but you can only fit this through here with this kind of margin, and there's no other hyperplane with that kind of margin that you can fit through here. All right. So this is also just for you to go through a little bit, but so these are the support vectors because they lie on the margin, and that's their importance, because you can for example remove all these 3 points and you would still have the same optimal hyperplane, while if you remove one of those, you would change the hyperplane. It would move to a different location. Right. We're running out of time a little bit, so I'm gonna skip forward a slide bit and show you. So this is what we achieve in the depression classification example, where we try to classify between depressed individuals and non-depressed individuals solely based off of the voice quality of the speaker. And we also get quite good at a PTSD classification, and these different kind of like all neutral, positive, negative kind of things. These are question contexts. So in a sense, we ask them different sort of questions. Like sometimes we ask negative questions, and they react differently to those, versus sometimes they react positive to some other questions. All right. These are just some basic conclusions about this, and I would like to end the voice quality assessment with another kind of interesting idea where we used voice quality classification for expressive speech synthesis. And one of the problems that you have right now, so Siri works pretty well. It can synthesize voices pretty decently. However, it doesn't express emotion that well. And one of the ways that we wanted to approach this was through voice quality classification, and we actually again trained a support vector machine. In this case, it was a fuzzy support vector machine, and in this case, fuzzy means that it gives you a label on the dimension of of breathy to tense, but it doesn't give you like breathy, tense, or modal, but it gives you like somewhere between modal and tense, something like that. So it's a continuous measure, okay? And so we use audiobook data to train our classifier, to actually to synthesize voice, or like to identify clusters of different voice qualities. And so we train our model on 20 speakers, 10 different languages, and about 50 sentences per person. And then we test our data on unlabeled audiobook data, and we have about 2 hours of speech, 2,000 utterances each of these guys, and we look at 2 books, Jane Austen's Pride and Prejudice and Mark Twain, Tramp Abroad. And so this is the approach that we followed. We take the audio, we do the feature extraction, we make the classification, and then we project the data points into this kind of like 3-dimensional breathy modal tense kind of cluster. And I have a few examples for that.
I never made a gasp before that came so near to suffocating me.
So that's an example from the breathy cluster.
I never have seen another dumb creature that was so morbidly sensitive.
That was a modal example, and now this is one of the examples that we identified to be in the tense cluster, and you can hear what the problem is already.
And then he says, "Why, I didn't hear it fall."
So it's a tense voice, but it's actually like this acted out kind of voice. So for this guy, if you want to synthesize speech, you would kind of generate this funky voice rather than like a suddenly tense voice for this person.
Every face was turned toward the center of attraction.
That's another breathy example.
Around about are green trees and grass.
That was a modal example. And
Jump ashore and take a turn round a tree and pass the bite board.
so that was another one of those tense examples. All right. So I think we have to go into a break and for 10 minutes, and then we start with the discussion session. The 2 people that are presenting first in slot 1, they are here. Okay, great. And for slot 2, we have the 2 people too. Maybe not. So you're alone? Is that okay? Okay, we'll help you out. All right. Cool. So see you guys in 10 minutes.